Our final shuffle for this video is shuffle 36, bottom row on the right. This is also a judicious Klondike, so it's a dealing out into 4 piles by way of the Klondike shuffle, but this time we will be stacking from right to left, and so we'll show you how to read that notation in just a moment. So let's go ahead and begin with our ordered packet 1 through 8 and perform our shuffle and see what new ordering results. So the judicious Klondike, this is where you take the top and bottom cards off as 1, put them down into pile 1 here, top and bottom off into pile 2, top and bottom off into pile 3, and then the last 2 constitute pile 4. Now the stacking is as follows. 4 goes on top of 3. That set of 4 will go on top of 2. That bigger set of 6 will go on top of 1. Now all that means is we're stacking from right to left. That's just a way to notationally represent the stacking of these 4 piles from right to left. Okay? So what is the new ordering we obtain? Well, it's 4, 5, 3, 6, 2, 7, 1, 8. Expressing this in Cauchy's 2-line notation, we obtain the following. The top row is always 1 through 8. In our case, the bottom row is 4, 5, 3, 6, 2, 7, 1, 8. We can convert this to cycle notation as follows. 1 goes to 4, so we have an arrow from 1 to 4. 4 goes to 6, so we have an arrow from 4 to 6. 6 goes to 7, so we have an arrow from 6 to 7. And then 7 returns back to 1, so it cycles around, completing a 4 cycle. Next, 2. Where does 2 go? 2 goes to 5, so we have an arrow from 2 to 5. And then 5 returns back to 2. So that completes a 2 cycle, also called a transposition. 3. 3 goes to 3. So we're looking at a fixed point. So whatever begins in position 3 will be returned to position 3 once this shuffle is completed. And finally 8. 8 is also a fixed point. So whatever begins in position 8 will return to position 8 after this shuffle is completed. If we color code our values, we obtain the following. Recall that the sets of position values of interest to us in the study of Bessey sequences are the following. The first set consists of 1, 4, 6, 7, which we've color coded black, and position values 2, 3, 5, 8, which we've color-coded red. In the case that the Bessey sequence is, quote, preserved, this represents that outcome, or if the sequence is inverted, then this represents that outcome. And just to remind you, an inversion occurs if the cards originally in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8 in some assignment, and vice versa. But looking at the color coding of our cycle notation here, we can see that inversion has not occurred because we have black 1 going to black 4, which goes to black 6, which goes to black 7, which wraps around to black 1. Red 2 goes to red 5, which wraps around to red 2. Red 3 gets assigned to itself. Red 8 gets assigned to itself. Now, one thing you may have noticed if you've gone through many of the videos in this series dedicated to Bessey shuffle diagrams, if we've ever had a shuffle that has a fixed point, where a card in one of the positions always returns to that position, if it is a Bessey shuffle, it must be that the Bessey sequence form was preserved, as is the case here. In fact, let's go ahead and just demonstrate that. So if we begin with the Bessey sequence 1001, 0110 and perform this shuffle, we should get this same sequence form back. So let's check that. So the judicious shuffle in which we stack from right to left is as follows. You take the top and bottom off as one, put them down for as the first pile, top and bottom off is one for a second pile, top and bottom off is one for a third, and then the last two become a fourth pile. And then we're stacking from right to left. Okay? And what we're expecting to see here is the same sequence form of 1, 0, 0, 1, 0, 1, 1, 0. And that is what we have here. Now, even though we get back to this Bessey sequence organization, it doesn't mean that the cards have not moved around, right? Because we know that most of them have moved around. Okay, so for example, the cards in positions 1, 4, 6, 7 have been moved around among themselves, which are the locations of the ones. Remember, the ones begin in position 1, 4, 6, 7, so those are moving around among themselves. Similarly, the 0 in the second position and the 0 in the fifth position switch places every time you perform this shuffle, whereas the 0 in the third position right here, this one right here, it stays there. It's a fixed point. Similarly, the 0 in the 8th position over here stays there. So 6 out of the 8 cards are genuinely moving around each time you perform this shuffle, even though the net effect is we get back to our original sequence form of 1, 0, 0, 1, 0, 1, 1, 0. And finally, if we take a look at our last shuffle diagram, so bottom row on the right, we observe the following. We know that value 3 and 8 correspond to fixed points. And I want to remind the reader that normally when we write cycle notation for a permutation, the one cycles or single cycles are typically not written down. And you can do that as long as you are aware of the size of the set of objects you're working with. So as long as we know we started with 1 through 8, you can safely drop these one cycles. Now down here we included them just to show you that the color coding makes clear that every value is returned to a value of the same color. Okay, so back here, so once again, fixed points 3 and 8. Now look at what happens with 1. 1 goes to 4, which goes to 6, which goes to 7, which wraps around to 1. So if we come over here to 1, we should have an arrow from 1 to 4, which we do. We should have an arrow from 4 to 6. There it is. And then we should have an arrow straight up to 7. And then we should have an arrow from 7 back to 1, completing that 4 cycle. And so those 4 values, 1, 4, 6, 7, constitute an orbit, as does the 2 values 2 and 5. That's an orbit of 2 objects. And then we actually have 2 tiny orbits consisting of just 1 value each. 8 constitutes its own orbit, as does 3. And before we leave Shuffle 36, let me just point out Shuffle 36, as indicated down here. Now, of course, now you can't read it. Shuffle 36 is the inverse of Shuffle 12 at the bottom of the screen. It's also identical to Shuffle 15. So why don't we just quickly take a look at those. Okay, so going back to Shuffle 12, the claim is that this shuffle here, the mange under over, is the inverse of Shuffle 36. Now we've seen this kind of thing before, where earlier we saw that the mange over under is the inverse of Shuffle 19. That was a Klondike shuffle, if you remember. So boy, I don't know how many people would believe that the mange under over and this shuffle 36 actually undo each other. That is really difficult to believe. But look, you can take advantage of that fact. So let me just demonstrate that it's the case. So if we begin with an ordered packet 1 through 8, if I perform the mange under over, which is one we've covered already, this is where you move the top card into your other hand, and then the next top card goes under. We're going to do this alternating under, over, under, over. So it goes under and then over, under, over, under, over, under. Okay, so we get quite a mess here, as you'll see. Okay, now amazingly, because we've just shown it here, the shuffle diagram for the mange under over is identical to the shuffle diagram for shuffle 36, except for the fact that the arrows go in the opposite direction. And that indicates that these must be inverses. Okay, so we've performed the mange under over. So let's go ahead and perform the shuffle that we've just introduced, shuffle 36, and apparently it will undo the effect of the mange under over. Okay, so shuffle 36, one more time here. So you Klondike one pair into like a pile 1, Klondike a pair into pile 2, Klondike a pair into pile 3, the last 2 go down as pile 4, and then remember for shuffle 36, we're stacking from right to left. Okay, and the claim is because these are inverses of one another, we should get the original ordering of the cards. So I challenge really anyone, watch the actions of the mange under over, watch the actions of shuffle 36, the judicious Klondike where you're stacking from right to left, and see if you can draw the conclusion that those two shuffles undo the effect of each other. Okay, and since we have inverses, that also means that we could perform shuffle 36 first, followed by the mange under over, and it will still reset the packet to its original order. Okay, so I thought I'd point that out. And then also you'll see that at the bottom of shuffle 36, there's a statement that shuffle is identical to shuffle 15. Okay, so what was shuffle 15? Shuffle 15 is just the ordinary Klondike. Isn't that interesting? Now this won't be as hard to see, I don't think. But this is the ordinary Klondike where you're stacking them on top of each other. In fact, if you think about shuffle 36 being equivalent to this one, it won't be as big of a leap to see that shuffle 36 should be the inverse to the mange under over. Okay, so why is this? Why are these two identical? Well, what does the Klondike shuffle do? This is where you take the cards, top and bottom off as 1. Okay, this is the first pair set down. Top and bottom off as 1. This is the second pair being set down. Top and bottom off as 1. Third pair, last 2 go on top. Isn't that the same action as doing this, which is what shuffle 36 is, where the bottom pair will be on the bottom, this will be the next pair up, this will be the next pair up, and then this will be the top pair of the pile if you stack from right to left. Okay, so I think that one can be puzzled through and detected that, oh yeah, shuffle 15 truly is the same permutation as shuffle 36. Okay, so let's do an application. I have here